So I'm going to discuss the geologic history of Yellowstone National Park. So just a few quick facts about the park is that it's the United States' first national park inducted in 1872. It is 2.2 million acres of land located mostly in Wyoming, but there are some sections in Montana and Idaho. It has over 5 mountain ranges and it's averaged at around 8,000 feet elevation. It has 2 large rivers, the Snake and the Yellowstone, and it is highly biodiverse. It actually has its own ecosystem, the Yellowstone ecosystem, and it was inducted as an international biosphere in the 70s and a World Heritage Site in the 80s. Here are a few pictures of the Snake River and the Moose Fall. It's called Moose Falls because there's lots of moose that go by there, and it is one of the waterfalls from the Snake River. Here are a few examples of some of the animals that you can find there. This is called a pronghorn. This is a snail. That's the Cecropia moth. There are some river otters, and there is a yellow-bellied marmot, which essentially is a giant rodent. To fully understand the history of the park, we'll have to go through a few vocabulary words first. So, layers of the earth, the crust, the mantle, and the lithosphere. So the crust is defined as the outer layer of the earth, so the top. So there are 2 types of crust. There's oceanic crust and continental crust. The continental crust is always less dense than oceanic crust. So oceanic crust, when the plates collide, will always fall underneath continental crust. So it will always subduct. The mantle is the layer in between the core and the crust. So the mantle is the layer of rock in between them. The lithosphere is a non-flowable layer of rock, so it's not liquid rock, in between the mantle and the crust. So the lithosphere essentially is cool enough to be solid mantle rock, but not high enough up to be crust. And it's important to note that it's rigid, but it can move. So plate tectonics, everybody knows a little bit about plate tectonics. They're more familiar as the years go on. Essentially, that lithosphere and that crust move. They move, there are plates, sections of crust and lithosphere that move around. And that it helps explain things like continental drift, supercontinents, we're all familiar with Pangea. It also helps explain volcanic activity as well as earthquakes. You'll notice that volcanoes are usually at the end of a plate boundary as well as earthquakes. So another important thing to know before we learn about the history is our hotspots. Hotspots are located at interiors of plates. They're not at plate boundaries. So they occur at the end of an inactive chain of volcanoes. So the most common one that we know is Hawaii, the Hawaii Islands. So essentially it has moved throughout the years. So essentially a hotspot is a mantle plume that the molten rock travels through and becomes liquid when it hits the lithosphere. And so the plate and the lithosphere move, but the hot spot stays the same. So as throughout time, it creates a chain of islands or a chain of land, and the hot spot stays where it is. So here are some hot spots. You can see that most of them are not located at a plate boundary. Yellowstone is right here. So you can see it's located sort of in the middle of a plate boundary. The last vocabulary word we have is a caldera. So essentially a caldera is during a large, violent volcanic eruption, the volcano will collapse on itself. And when it collapses on itself, it will create a large depression, which we call a caldera. And it can fill with water and become a lake. A really famous one is Crater Lake, which actually isn't a crater, it's a caldera. So back to the beginning of the history of Yellowstone National Park. The earliest rocks at Yellowstone can be traced back to the Precambrian era around 2.7 billion years ago. So it is believed around the Cambrian era that all of Yellowstone was underwater. And this left behind sediments, which created some of the sedimentary rocks that we see today. As well, it was the first signs of life at Yellowstone. Next, Yellowstone started to form its mountains, so around 75 million years ago. There was a time in geologic history referred to as the Laramide orogeny. Orogeny means mountain building, where there were tons of mountains being built, and this is when most of Yellowstone's mountains were built. And They're formed when plates collide. And so it not only helped form its mountains, but other geologic and topographical features at Yellowstone, which are things like faults where the land slips, or inclines and synclines, which are U-shaped rock formations. So the mountains that we see today are the results of all the geologic features we just talked about, as well as the continued pulling and stretching and rise and fall of the landscape that have occurred for the remaining 10 million years or so. Yellowstone was also glaciated, meaning that glaciers came in and helped carve out the land as well as deposit debris that they were carrying. Yellowstone also has canyons and waterfalls that were formed over the years through eroding water and from erosion from water, and the Grand Canyon, Yellowstone has its own Grand Canyon. It was actually formed by the erosion from the Yellowstone River, as well as some volcanic activity. Here we just see a picture of a lake, the mountains, and an island at Yellowstone. So one of the really, really cool things about Yellowstone is it actually has volcanic activity. So most of Yellowstone, or actually all of Yellowstone's volcanic activity comes from a hotspot. It lies at the end of a strand of calderas called the Yellowstone Hotspot Tract. Most of Yellowstone's significant volcanic history occurred recently from a geologic standpoint, so meaning around 16 million years ago to around 630,000 years ago, with significant eruptions stopping around 70,000 years ago. The Grand Canyon of Yellowstone also shows evidence of past volcanism. The river's flow is a view of past lava flows as well as other thermal activity. So Yellowstone lies at the end of a string of calderas that started around 16 million years ago, but the three most important calderas that we're going to talk about came from around 2 million years ago. So there are three distinct large eruptions that have impacted the park and have formed some of its features that we know and see today. So the largest eruption, the first eruption also, was 2.1 million years ago. They've named it the Yellowstone caldera. It was centered in the western section of Yellowstone National Park. It's in an area now called Huckleberry Ridge, and it produced over 600 cubic miles of ash. So if anybody remembers the Mount St. Helens eruption, that's over 4,200 times the amount of ash that was produced from the Mount St. Helens eruptions back in the United States. So the second and smallest is called the Island Park caldera, and it also overlays in Huckleberry Ridge. They all overlay each other. And the most recent, and the second largest, was the Lava Creek eruption, and it overlays Huckleberry Ridge 2, and it created the Yellowstone 2 caldera. And today, the Yellowstone 2 caldera holds the world's largest alpine lake, the Yellowstone Lake, in a portion of its caldera. So here is a picture of all three calderas overlapping each other. Here we have our largest in the pale color, our smallest, and our youngest. Today's volcanic activity, which is some of its most famous at Yellowstone, so there are over 10,000 thermal features at Yellowstone with 300 to 500 geysers, which is over 55% of the world's geysers. So I know places like New Zealand are known for their geysers, and the United States holds over 55% of the world's geysers. So they also have hot springs, mud spots, and fumaroles. Fumaroles are steam vents. So a little bit about how a geyser works. So a geyser is essentially, or is defined as episodic, So episodic means that it occurs frequently and that it occurs more than once. So a geyser forms when the earth is fractured, so fractured meaning it's cracked. So the earth is cracked, and water fills up with it, and it gets hotter and hotter as it goes down and pressure increases. This pressure and this heat allows the water to stay at a liquid temperature even at degrees over 400 degrees Fahrenheit. So it stays liquid when it's really, really hot. This causes itself to push itself up to the top, and it creates steam rapidly, and then creates water rapidly, and then shoots out of the top, and then creates the motion that we see today of the water spitting out of the top. So hot springs are exactly what it sounds like. It's a bed of hot water. One of the coolest hot springs at Yellowstone is called Mammoth Hot Springs. Mammoth Hot Spring has slightly acidic water and erodes the earth around it very quickly and dissolves it into calcite limestone. The limestone is deposited very, very quickly and creates these really cool structures that you can see right there. It moves very fast. It deposits over 8 inches of sediment a year, which is a lot of sediment. Mud spots are basically water has dissolved clay and silica. The water and the clay and silica mix together and they create mud, and then it creates bubbly mud. Our last thermal feature are fumaroles, which are steam vents, which work almost exactly the same way geysers do, except for they don't have as much water. So all it can produce is steam. It also has a very distinct loud hissing noise when it comes out of the earth. This is the end. Are there any questions? This is the Yellowstone Grand Canyon from the front view, and this is a view of it from the top. Any questions?
I got a question.
Yeah?
You said the mountains were created by a fault.
No.
You said it was two plates colliding, so it'd have to be on a fault, but it's nowhere near a fault line.
Now.
So did it move over?
Well, I'm not sure, but mountains are not, like, they're created from, like, the earth, like, pushing and pulling, right? So if you look at where Yellowstone is, like, so they formed at this time when the earth doesn't look like it looks like today. So the earth, like, pushed and pulled and slipped and fell and did all that stuff over time. So even though it's not located directly at a plate boundary, it's still located enough where it could have, like, topographical features changing. Anyone else?
No, that was it.
Okay, thank you.